Hello friends, and welcome to the another lecture of information theory and coding in Tech communication engineering. So today the topic is Markov chain for stochastic processes. So Markov chain, stationary as stochastic process is said to be stationary if probability of, say, for the x1 is x1, this is the outcome of sequence, x2 is x2, and capital X of n is equal to small f x n. So the probability will be for 1 plus L will also be x1, 2 plus L will also be x2, and n plus L will also be xn for every n and every shift. So this is the shift. L is the shift. So the joint distribution of any subset of the sequence of random variables is invariant with respect to shift in the time phase. It means the sequence will remain the same for time shift. Markov chain. A discrete stochastic process x1, x2 is said to be Markov chain or Markov process for n is equal to 1, 2. So if x of n plus 1 will be equal to capital X of n1 plus 1 will be equal to x of n plus 1, and x of n will be equal to x of 1, x of capital X of n minus 1 will give x of n minus 1. So x of n plus 1 will be equal to this, and x of n is equal to smaller x of n. So the joint PMF can be written as P of x1, x2 up to x of n will be equal to P of x1 into P of x2 upon, that is the probability of getting x2 when the input is x1, and similarly for probability of getting x3 when the input is x2, similarly for xn when the input is x of n minus 1. So the Markov chain is said to be time invariant if the transition probability x of n plus 1 which depends on the previous input. So if x of n is equal to b or x of n is equal to a, so x2 will be b and x1 will be a for all values of a. We will assume that the Markov chain is time invariant. Xn is called state at timing. So xn is nothing but the state at time n. A time invariant Markov chain is characterized by its initial state and probability transition matrix, that is PTM, will Pij, where Ij will be from 1 to m, where Pij is equal to probability of x of, so x of n plus 1 will be j and x of n will be I. So at the PMF, that is the probability transition matrix, at time n plus 1 will be the probability of extent of n plus 1 time will be summation of probability of x of n and probability of p of xn and n plus 1. So a distribution on the states such that the distribution at n time n plus 1 is the same as the distribution at time n is called stationary distribution. So you can see the distribution at time n plus 1 is the same as the distribution at time n is called stationary distribution. Consider a two-state Markov chain with the probability transition matrix. Now probability transition matrix has some characteristic. So the sum of each row should be equal to 1, that the probability should be 1, and these are called the next states rather we can say. So it's stationary distribution and entropy. Let mu1 and mu2 be the stationary distribution. So mu1 will be equal to 1 minus alpha into mu1 plus beta into mu2. Similarly, mu2 will be equal to mu1 into alpha and 1 minus beta into mu2, and the summation of mu1 and mu2, the stationary distribution should be equal to 1. So entropy rate. The entropy of a random process x of I is defined as h of x limit n tends to infinity 1 upon n h of x1, x2 up to xn. So conditional entropy, the entropy of a random process is defined as s dash x limit as n tends to infinity h of x of n by x of 1 and x of 2 up to x of n minus 1. If x1 and x2 are IID, random variables, then h of x will be equal to limit n tends to infinity h of x1, x2, x of n upon n, and limit n of x of x1 upon n, that is h of x1. If n x1 and x2 are independent but not identical distributed, like in the previous case, identical distributed, so h of x will be in that case n tends to infinity 1 upon n summation of I1 to n h of x of I, that is h of x of I1, x1, x2 up to x of n. So we choose a sequence of distribution on x1, x2 such that the limit does not exist. So the theorem for a stationary stochastic process, h of n, n minus 1 up to h1 is non-increasing in n and has a limit s dash of x. So here we can see that x of n plus 1, x1, x2 and up to n. So it is less than equal to h of n plus 1, x2 and x of n. This is by conditioning reduced entropy, and then this is the stationary. Since h of n oblique h of n minus 1 is a non-negative and decreasing, it has a limit s dash x. So it has the limit, it has proved that h of this is a non-increasing in n and has a limit at s dash x. For a stationary stochastic process, both h of x and s dash x exist and are equal. So by chain rule, we can prove that this is the entropy rate, is the time average of the conditional entropies. Since the conditional entropies has a limit s dash x, we conclude that the entropy rate has the same limit by the theorem of Cesaroni. So this was all about the Markov chain and the entropy rate, and we'll proceed with our lecture. Thank you.